Thank you. And I want to make it clear that like I did async IO wrong. Like async IO as itself is not like wrong. It's easy just to mess up. All right, so first, who am I? So I'm an SRE. I work at Spotify, which is a streaming music company. And what an SRE does at Spotify, or site reliability engineer at Spotify, as it varies wildly between companies. It's a combination of back-end development, where my team and I run a lot of infrastructure-based services, and a little bit of DevOps and system administration. But essentially, if Spotify goes down, I'm usually the one to get paged. So I'm the one firefighting a little bit. I'm also our FOSS, or open source evangelist at Spotify. I help a lot of teams release their projects and tools under the Spotify GitHub organization. And lastly, I help lead PyLadies, which is a global mentorship group for women and friends in the Python community. All right, so async IO. It's the concurrent Python programmer's dream, right? The answer to everyone's prayers. So the async IO module has a lot of layers of abstraction, allowing developers as much or as little control as they need and are comfortable with. A simple hello world-like examples show how simple it can be. I mean, just look at it, it's so simple, right? But it's easy to get lulled into a false sense of security. And also, this isn't that helpful when you do want to start programming in async IO. So this is all like fake news, right? We're led to believe that we're able to do a lot with the structure of like async and await API. Some tutorials, while great for the developer to get their toes wet, to try and illustrate real-world examples, but they're actually just a beefed-up hello world kind of example. Some even misuse parts of async IO, the interface, allowing one to easily fall into the depths of callback hell. Some get you easily up and running with async IO, but then you may not realize that you're actually not doing it correctly or exactly the way that you want, or only getting you parts of the way there. While some tutorials and walkthroughs do a lot to improve upon the basic hello world examples, usually it's just a simple like web crawler. And I'm not sure about others, but I don't build web crawlers at Spotify. So sure, we might need to make a lot of HTTP requests that should be non-blocking. But these services also have to interact with like a pub sub, maybe measure progress of actions initiated from those pub sub events, handle any incomplete actions or external errors, and then deal with like pub sub message release management, measure service level indicators, and send metrics. So there's a lot that we can do, or that we might need to do asynchronously. And we might need to do this using non-async IO friendly dependencies. And so using async IO, at least for my team, got pretty difficult really quick. So I'm going to provide you with like a real world example that actually comes from the real world. So recently at Spotify, we built a service that does periodic restarts of our entire fleet of instances. Has anyone heard of Chaos Monkey? Some people, yeah. A Chaos Monkey is an open source tool from Netflix that kills hosts to see how reliable they are. And at Spotify, we just built something that just restarts them. And so this talk, we're actually going to build our own Chaos Monkey. We're going to build what's called mayhem mandrill. Mandrill is a type of monkey, I don't know, it's cute. So what we're going to do is we're going to listen for a pub sub message and then restart a host based off of that message. And then as we build the service, I'll point out traps that I may or may not have fallen into myself. And this essentially will become a resource that like a year ago Lynn would have liked to have read. So we'll start off with some foundational code, and this gets direct inspiration from async IO's tutorial documentation. And so we have a publish a coroutine function that generates a random sort of host ID, and we give it a number of messages that we want to produce, and it just produces that amount of messages. And then once we're done producing all the messages that we tell it to, it will just produce one final one, none, to tell it that it's done. And then we have the consumer on the other side of that, where it consumes from the queue, and it just pulls a message from the queue. If it pulls a none message, then the publisher is done. And then it will consume the message and do some super unhelpful simulation of I/O operation on a message. And then using the latest 3.7 syntactic sugar, we can just do asyncio.run on both of these coroutines, and we'll get something like this. So this works off of that asyncio official tutorial. Basically, we publish messages and then we consume them. And we're going to work off of this. So far, we don't actually have a running service, you might have noticed. It's pretty much a pipeline job right now. So we run the publisher and then we run the consumer. But before 3.7, we had to set up and tear down the loop ourselves. Note that it is a good habit to sort of clean up that loop when we're done, since we've created it. So this is effectively the same sort of thing that asyncio.run gives you. But since this is a service, we don't want it to just run once. We want to continually consume from a publisher. And unfortunately, there isn't a decent way to do that in 3.7 if you're not an HTTP server. So we're going to stick with this 3.6 approach, where we create 2 tasks out of a coroutine, and then schedule them on a loop. And then we'll just start the loop and then tell it to just run forever. So then when we run this code, we publish 5 messages, and then consume 5 messages, and then we hang, obviously, because there's no more work to be done, right? So to stop the process, we have to interrupt it with Control C or some a signal, kill int or something. So this is nice and ugly, right? And you might notice that we actually never get to a loop.close, or it's kind of hard to see. So we have to run it a little bit defensively. I'm going to fake an error, essentially, to kind of show how this works. So this is where the consume function is now. And then if it's if the ID is 4, then I'm just going to raise some stupid little exception. And so if we run it as is, we get a exception was never retrieved, which you can see there, from our faked exception. And this, admittedly, is a part of the async.io API that is not that friendly. So if this was synchronous code, it would raise the error and then just fail. But here, it's still running, and we still have to kill it ourselves. So to deal with this, as advised by the async.io documentation, we need a little wrapper around the coroutine to consume the exception and then stop the loop. So we have this. I made this little top-level wrapper to run and handle exceptions from those coroutines. And we're just deciding to force our service to crash if we get any exception, and then stop the loop. So we update our main section. We wrap publish and consume coroutines with the handle exception. So then when we run our little script, we get something a little cleaner. And that's also a bit more clear. So to wrap up so far the initial setup, for setting up an async.io service, be sure to surface the exceptions from your coroutines, and then also to clean up what you've created. I'll expand on both a bit later. But you might notice that we're still sort of blocking. We're not really asynchronous. So I've seen tutorials make use of async in a way that it does not block the loop, but we're still iterating through tasks serially or sequentially, effectively not really adding concurrency to the program. So if we take a look at where we are now, so this was adapted from that tutorial, and so we're going to kind of change it a little bit. The event loop itself isn't blocked here, but we're still publishing 1 through 5, or 0 through 5, or whatever. And then we're consuming all of them one by one. And so while this technically is a working example of a pub sub-like queue with async IO, it's not really what we want. It's no different than synchronous code. So whether we're building an event-driven service, like this mayhem mandrill that we're doing, or it's a pipeline job or something like that, we're not really taking advantage of concurrency right now. So we're going to start by adding concurrency to the publisher. And so again, this is where we're starting with. And then instead of the range, I'm going to throw in a while true loop, because we don't know how many messages that we could have, or we can just produce unlimited ones. I've also added sort of a creation of a unique ID for each message produced, since there's no longer a simple like 1 through 5. And then one other thing is I'm going to remove the await for the queue.put for the message, and then replace that with a create task. The async IO create task will essentially schedule the coroutine on the loop to be ran without blocking the rest of the function, rest of the for loop. So while the create task will actually return a task if we cared about that, but we just want essentially to like queue it on the loop and get it to be done, and then continue on producing those sorts of messages. If we left the await here, I want to make it clear that we would essentially block everything else after that. This isn't an issue with our current setup, really, but it would be if we sort of limited the size of the queue itself. Then the await would be awaiting on space to free up within that queue. So by using create task, this tells the loop to put the message on the queue as soon as possible, and then allows us to continue publishing messages as we need. So then when we run something like this, we're happily creating and publishing these messages. But if you notice, there's that keyboard interrupt. Very nice, very clean, not really, and it's not actually caught. So we can quickly clean that up a little bit by catching the keyboard interrupt. It's a quick band-aid, which I'll explain further on. But for now, running this, we see something a lot cleaner when we interrupt the process. So it's probably hard to see its concurrency right now. So what I'm going to do is have multiple publishers. And to make it a bit more clear, I'm going to just send another argument to the publisher for an ID so that it can be logged when it's publishing a message. And then in my main section, I'm just going to create 3 publishers and then quickly run that. And you can see that there's concurrency among the publishers. So for the rest of the walkthrough, I'm just going to remove the multiple publishers and only have that one, because I just wanted to convey how it is actually concurrent and not just non-blocking. All right, so time to add some concurrency to the consumer. For this, the goal is to essentially consume a message from the queue and create non-blocking work based off of the newly consumed message. In this case, like restart an instance. The tricky part is that the consumer needs to be written in the way that a new message from the queue is separate from how the message is handled. We have to, in other words, we have to simulate being event-driven by regularly polling for a message, since there's no way to trigger work based off of a new message available in the queue. Basically, there's no way to be like push-based. Looking at the consumer again, if we just sort of remove the if message is none part, because the publisher won't ever be like done, we now can also replace that async io.sleep with some like actual work of restarting the host, which is just moving the async io sleep. Super helpful, I know. But we write the coroutine function that, so we write a coroutine function that's mocking the restart work that needs to be done on any consume message. And we're separating out the faked IO work that's being done on the message versus actually consuming that message. We also create a task out of restart host. For similar reasons with the publisher, we don't want to unnecessarily block the consumption of messages. But we do leave the await here for the queue.get. It makes sense to block on this because we can't really do anything if there are no messages to consume. I should note that when I say that the await blocks, it doesn't block the event loop. It just blocks the further the work or the logic after, defined right after within the scope of the function. So then re-adding the consumer coroutine to our main section. We're then publishing and consuming and restarting messages whenever they are available. We may want to do more than one thing per message. For example, maybe we'd like to store a message in a database, maybe for potential replaying afterwards, as well as initiate the restart of a given host. So we will make use again of the async io create task to schedule on the loop, basically chucking it over to the loop to execute when it can. And then running it, we see that for every message there either will be a restart or a save first, showing some asynchronous work going on because there's no order. We also don't block the consumption of messages with the work that we do generate from that message. So to illustrate this a little bit better, we can switch the create task for save and restart and await them instead. And so here we see that we don't necessarily block the event loop, but the await save blocks the await start restart host, which blocks the consumption of future messages in the next iteration. So there's a very clear order here, and we're not taking advantage of concurrency when we could. But maybe you do want your work to happen serially or sequentially. You might not need concurrency for some asynchronous tasks. These tasks don't necessarily need to depend on one another, completely like sidestepping the complexity of should I restart a host if a message fails to save in the database. We're just going to sidestep that for a second. So maybe you want to restart a host that has an uptime of more than 7 days. Or maybe you should check like a balance of an account before you actually take money out of it. So needing code to be serial or sequential, to have steps or dependencies, it doesn't mean you can't be asynchronous. The await last restart date will yield back to the loop, but it doesn't mean that the restart host will be the next thing that the loop executes. It just allows other things to happen outside of this coroutine. So if we can put all of this message logic into like a separate coroutine function, so we don't have to block the consumption of messages. And then saving a message doesn't need to block a restart if needed, so we're just going to return it back to a task as well. So for simplicity, I've just removed the checking of the last restart date logic into the restart function. Just pretend that I did that. And so we've been pulling messages from a queue and found out work based off of that. But perhaps we also need to perform like finalization tasks on that message. For example, we might need to acknowledge that message that we're done with it so that it doesn't get redelivered like a typical pub sub would do. So we currently have 2 separate tasks, save and restart host. We want to make sure that both are done before the message is cleaned up. We could go back to the sequential awaits, since that's a very direct way of manipulating the ordering that we need to happen. But we could also use callbacks on a completed task. So what we therefore want is to somehow have a task that wraps around two coroutines of save and restart, since we have to wait for both of them to finish before we can clean the message up. We can make use of asyncio.gather here, which returns a future-like object for which we can then attach a cleanup callback function to via like the add done callback method. So then we can just await the future in order to kick off the save and the restart coroutines, and then the callback of cleanup will be called once those two are done. So when we run it, we can see that once we saved and restarted the host, cleanup will be called and signifies to signify the message is completely done. And then we've still maintained appropriate concurrency. So I personally have an allergy to callbacks, as well as perhaps we need the cleanup to be non-blocking as well. So another approach could just be await both the async.gather and then the cleanup right after that, since the order still does matter. Let's see, so let's say that the pub sub will redeliver a message after 10 seconds if you didn't say ACK, or if you didn't say, hey, wait another 10 seconds, like if you didn't extend that deadline. So in order to do that, we need to have sort of a task that monitors everything that's kind of going on. So while our tasks are working to restart hosts and to save pulled messages, we need to have another coroutine that manages the extension of the deadline of the message. And then once they are done, we should stop extending that deadline and then go ahead and clean up that message. So one approach is to make use of asyncio.event primitives. This event instance essentially provides us with a Boolean flag. Our extend coroutine will essentially loop while that flag is not yet set, continually extending the message deadline until we're done. And if we update our handle message function, we'll create an instance to give an event instance to give to the extend coroutine, and then create a task out of that, basically fire and forgetting that. And we still await the asyncio.gather, and then once we're done, we will queue the extend function to start the cleanup process. We'll set that Boolean flag. And so then running this, we can see that we're extending while work continues, and then cleaning up once done. Now, if you love events, you could adapt this just a little bit to make use of the event.wait coroutine. And so then cleanup would be its own task again that you could fire and forget alongside with the extend coroutine function, making it a bit more logical to read so that cleanup isn't called within the extend, but from the same place that message-related tasks are being controlled. So quick TLDR of this section. Async.io is definitely pretty easy to use, but being pretty easy doesn't automatically mean that you're using it correctly. So you can't just throw async and await keywords around blocking code. It's actually just like a mental shift, a mental paradigm change, both in needing to think of what work can be farmed out, what can be concurrent, and what dependencies there are, what needs to be sequential, and where your code might benefit from being asynchronous. But having steps in your code, like having first A and then B and then C, may seem like it's blocking when it's actually not. So sequential code can be asynchronous. For instance, I might be calling customer service for something, and then while I'm waiting to be taken off hold and to talk to them, I can like put my phone on speaker and then like pet my cat while I'm waiting for them. So I might be like single-threaded, but I can still do like multiple things at once. And I have to admit, this sort of thing was not immediately obvious to me and my team when we first started building our own like mayhem mandrill. So maybe it's obvious to some other folks what like asynchronous and concurrent is in Python terms. It wasn't to me. So there we go. Okay, sorry, we're good. Thank you. I apologize. All right, now for some graceful shutdowns. So earlier we tried the try except finally around our main event loop. Often though, you'll want to have your service gracefully shut down if it receives any sort of or certain signals, like cleaning up database connections or stopping of consuming messages, maybe finish responding to current requests while not accepting new requests. So if we happen to restart an instance of our own little chaos monkey-like service, we should clean up the mess sort of that we've created before exiting out. We've been catching the commonly known like keyboard interrupt exception, like many tutorials and libraries show. So if we send our program another signal other than SIGENT, like SIGTERM, we see that we actually don't reach the finally clause that we have. So we should see something like cleaning up. It should also be pointed out that even if we were to only catch the SIGENT signal, it could happen outside of that catching exception, potentially causing the service to end up in an incomplete or otherwise sort of unknown state. So instead of like catching keyboard interrupt or other signals, we can use actually a signal handler on the loop itself. So we define this shutdown coroutine that will be responsible for doing all the necessary like shutdown tasks. So here I'm just simulating the closing of database connections, returning messages from PubSub that's not acknowledged, so that maybe they can be redelivered and not drop. And then we're collecting all the outstanding tasks with the exception of this specific like shutdown task itself, and then canceling them. We don't necessarily need to cancel pending tasks. We could just collect and then allow them to finish. We may also want this opportunity to flush any metrics that we've collected so that they're not lost. So since we have the loop.stop here in the shutdown, we can remove it in our earlier wrapper coroutine function. We no longer needed to pass the loop and don't need to stop it here. So then if we update our main section, so this is where we are now, and then adding the signal handling, we first set up our loop and add the signal handler. I also removed the keyboard interrupt catch since that's now taken care of in the signal handling. And then running this again, we see that we do get to the finally clause of cleaning up, a lot nicer. But it looks like we hit caught exception twice. And this is because a waiting on the canceling tasks will, in essence, raise a canceled error, which is to be expected. And we can handle that a little bit better in our handle exception coroutine. So within this coroutine, we can just add a catch for canceled error exception so that we can differentiate from others. So now that it's not just some random error that's canceled, we actually get some context and that coroutines are canceled. You might be wondering which signals to react to. And there is no standard. Basically, you should be aware of how you're running your service and handle accordingly. It seems like it could get messy with conflicting signals, especially when you add Docker into the mix. So maybe Docker, you can send a term signal to Docker for a graceful shutdown, but then if you have Nginx running in that, that'll be a hard exit. Another misleading API in async IO is the shield. The docs say it means that it will shield a feature from cancellation. But if you have a coroutine that must not be canceled during shutdown, async.io.shield will not help you. So this is because the task that async.io.shield creates gets included in the all tasks method call, and therefore receives the cancellation signal, just like the rest of the tasks. To help illustrate this just a little bit, we have a simple async function along with a long sleep of a full minute that logs a line to say done. If we want to shield from cancellation with async.io.shield, running this and canceling after a second, we actually don't see that done log line after all. It gets immediately canceled. And I'll be honest, I could not get async.io.shield to work under any circumstance. So I might just be dumb, but it's definitely not working in regular shutdown case. So a quick wrap up of the graceful shutdown parts. We don't have any nurseries in async.io core to help clean ourselves up. It's up to us to be responsible with how we close up connections, the files that we might have opened, or respond to outstanding requests. It's up to us to leave things how we found them. Doing our cleanup in the finally clause isn't enough, though, since the signal could be sent outside of that try except clause. So as we construct that loop, we should tell how that loop should be deconstructed as soon as possible to ensure that all our bases are covered and not leaving any artifacts around. And then finally, we need to be aware of when our program should shut down, which is closely tied to how we run our program. If it's a manual script, then SIGINT might be fine to respond to. But if it's demonized within Docker, then maybe sigterm might be more appropriate. So you might have noticed that while we're catching exceptions on the top level, we're not paying any mind to exceptions that could be raised from within the coroutines like restart host and save, etc. So to show you what I mean, we can fake an error where we can't restart a host. And so running this, we see that one of the hosts couldn't be restarted. And while the service didn't crash, and it did save that message to the database, it didn't actually clean up and act that message. The extend, the message deadline, just kept spinning. We're essentially deadlocked on this message. So the simple thing to do is within handle message itself, we can add return exceptions equals true into async.io.gather. So rather than completely dropping the exception, it's returned along with successful results. So while we don't see any tracebacks, nor are we perpetually extending messages, when running this, you actually don't see where errors are occurred now. But we do eventually clean up the message. So it would be nice to actually see which finished tasks raised an exception. So we can do that by adding a done callback to async.io gather feature. But as I said, I'm allergic to callbacks. So we can just process the results of the gathering tasks afterwards. For me, that actually makes more sense to understand what's going on. So then after the async.io gather returns, we can just separate out the successful responses from the errors. And so now running this, we can see that errors are indeed logged. But again, even though the task errored out, it doesn't block it from being cleaned up. Quick TLDR of the exception handling. So exceptions won't crash the system unless you tell it to. They might go unnoticed, and so we need to account for that. So I personally like using async.io.gather because of the order of the return results are deterministic. But it's easy to get tripped up with it. So by default, it will swallow exceptions and happily continue working on the other tasks that are given. So if an exception is never returned, weird behavior can happen, like forever spinning on an event. So I'm sure, as with folks starting to use async I/O, they've realized that async and await starts infecting everything else among the code base. Basically, everything needs to be async. And this isn't necessarily a bad thing. It's just forces a shift in perspective. So we'll start with mixing synchronous code with async, since sometimes you depend on libraries that are not yet async I/O friendly. And so let's say we have a non-async function that we need to call from our synchronous code and still be async. So to do this, we need to rework our async consumer just a little bit, but not much is needed. Here we're just making use of the thread pool executor to call the synchronous handle message, and then just creating a task out of that. But sometimes that's not enough. Sometimes a third-party code will throw a wrench at you. So if you're lucky, you'll be faced with a third-party library that also does threading in the background and is also blocking. So for example, I'm quite annoyingly familiar with the Google PubSub Python library. But it's awesome because it makes use of gRPC under the hood with threading, but also blocks when we're opening up a subscription. So the library requires a non-async callback for when a message is received. So it kind of like looks like this. Here, the client.subscribe from the Google Python library is multi-threaded. You can't really see, but it's under the hood. It makes use of, as I said, gRPC for like bidirectional communication, and removes the need to periodically pull messages, as well as it maintains the extending message deadlines for you. It might be confusing to handle this, knowing that there's threads in the background, but it's pretty similar to handle non-async code, as you would with non-async code. So we'll just use the run in executor that we did before, with some small tweaks to our consume coroutine. So the run in executor returns a future object, and we can just simply like await on that. I'd also like to prove that this is non-blocking, and we can add like a dummy coroutine to the function to be add a dummy coroutine to our process, so it runs alongside our consume coroutine. And then we have like a simple like main function to start both of them off. And now running this, we see that things are being consumed and something is being ran. All in all, though, as I said, the approach is similar. The approach to running threaded code with async I/O isn't much different from non-async code, until you realize that you need to call asynchronous code from threaded code or from non-async code. So we currently just ack the message once we received it, but that's not necessarily what we want, right? We want to restart the host and save the message to the database. So we have to somehow call asynchronous code from our non-async function from that separate thread. And this realization was pretty embarrassing to me, so bear with me. We'll first attempt to use the async I/O API that we're familiar with and update our synchronous callback function with creating a task via the async I/O create task from the handle message coroutine that we've defined already. And I've moved the message.ack since we're taking care of that in our handle message coroutine that was defined earlier. But we don't get very far, obviously. So at this point, we're in like another thread, and obviously no loop is running in that thread. It's only on the main thread. So again, embarrassing realization. So if we take what we have right now and update our function to give it the main event loop that we're using, maybe that could work. And so it looks like it works, but it's actually deceptive. We're just kind of lucky. And I'll show you why. So if we share some object between the threaded code in the callback and the asynchronous code when handling the message, we see that we've essentially shot ourselves in the foot. So we were going to create like a shared queue that our synchronous function will add to from one thread, and then we'll read it off in another thread, in our main thread, basically, to continue processing it. And so running it seems a little bit funky. We consume messages from the external pub sub, and that's in another thread, but we add it to the queue. But then our log line that is supposed to be getting from the global queue, we never see that. So it doesn't look like we actually go beyond just consuming and adding to the queue. To illustrate this a little bit better, if we add a line to add to queue coroutine to print the queue size as we're adding to the queue, you can see that the queue is just like ever growing, and in fact that we're not reading from it. And I'm sure some of you might see what's going on here. We're not actually thread safe. So instead of creating task for the main event loop from a different thread, we can make use of run coroutine thread safe to see what happens. And this like thread safe API should give a clue to what's happening. So this actually unblocks us, and we finally sort of have it. We're consuming from an external pub sub on one thread, and then processing the message as we need, like restarting the host on our main event loop thread, so two different threads. It is really embarrassing that it took a while for me to realize this. So in my opinion, it isn't really that difficult to work with synchronous code within async IO. You just make use of like the thread pool executor, which essentially creates an awaitable out of asynchronous code, so that we can treat it very similarly to our coroutines. However, it gets difficult to work with both threads and async IO, particularly when sharing some sort of state between one thread and like the main event loop thread. So if you must do something like that, then use the thread safe APIs that async IO provides you. Yeah, it probably took a couple months for me to realize that I was essentially blocking myself with this. In essence, this talk is something that I would have liked a year ago. So I'm speaking to like past Lynn here, but I'm hoping that others will sort of benefit from my learnings and not just a simple web crawler tutorial. Thank you.
Thank you. You're the first one. No.
Oh. I can use both. Thank you very much for your talk. It was super useful. I wish I could travel back in time 3 months right now and rewrite everything. I have a specific problem with the exceptions because I wanted to use Sentry, but as the exception is not really being captured, it's like you get the text representation of the traceback, but nothing more. I cannot really do anything about it. Do you have some advice?
Can't you use the, you can answer that.
What exactly is your problem? Because that's exactly what I do. I have this handler result thingy like her, and you just pull in the Sentry reporting into it. So you make like try except, and then you report it to Sentry. So what is exactly your problem? What doesn't work?
Yeah, I can repeat it again. I'm probably doing everything wrong.
Yeah, I actually have never used Sentry, so I don't know even how to work with it. Sorry.
Okay, thank you. I have a question. For example, I have a little Django application what use Celery for sending emails. And now, after your presentation, I want to throw down the Celery and use async IO for sending emails. But as I see, when I just use async IO create task, I will get exception that no loop is running. So maybe you have an experience to integrate async IO with Django.
I don't actually. Does someone else have? I don't even know if Django is async IO friendly. It is? All right. I use AIO HTTP for like my servers and stuff like that.
You should try a project called Django Channels, which integrate Django and asyncio, and you got like WebSockets for free.
Do you know the author of this project?
I am co-author that.
Okay.
Any other questions?
More questions.
We got a couple questions over here.
Yeah, my question is a bit silly. You're using like for your project like the pops up methodology, pops up pattern, but why? Like, I know you don't like callbacks, but like just like in my mind I was like thinking if you would use like RX Python or some other like reactive framework, it would be a little more easier to read and, you know, to conceptually grasp. Like, I think I just didn't get why you used like pops up. Like, why do you need like separate event channel for, you know, for just starting and like restarting servers? Because, you know, there's like...
So, I guess maybe some context is my company is all on Google Cloud. And so we have to use a lot of their tools. So when we want to, it's a whole separate system that schedules the restart of an instance. So we don't restart the whole fleet at once because that would be detrimental. So we restart like only a small number of hosts, like every hour or something like that, and to not take down any one service or microservice. And we schedule that by saying, all right, it's okay to restart this host, and we submit a message to PubSub for which our little chaos monkey-like thing consumes from. So
Yeah, that makes sense, but thanks.
Thank you for the talk. What are your thoughts on adding a nursery-like mechanism to async.io, but not as a part of async.io, but as a third-party library? Is it even possible?
you're like referring to like Trio and stuff?
Something like that.
Yeah. I think you picked up on my little nursery hint in my talk, but I think it's useful. I don't know how that would look like, and I haven't actually been able to use like Trio or some other thing, but I think it'd be very handy. But I also think we should probably work on cleaning up some of the APIs in core async.io first, like the shield like doesn't work, and some of the shutdown behavior itself doesn't work as you'd expect in 3.7. So I want to fix that first. But I think nursery as a concept would be really, really beneficial. I don't know how that would look though.
Thanks.
More questions?
Seems like no questions.
All right. I'll be around if more people want to talk.
Then thank you.
Thank you.